Hey guys, so today's lesson is kind of a one-off lesson, as I mentioned the other day. You could really fit it in anywhere after you do differential equations, which we did quite a while ago. So it's one of those things where, like I said, it's a one-off. And so the notes I'm going to do today, what I tried to do was find four problems from past multiple choice AP questions and just kind of work through them so you could see kind of the questions that they ask when they're dealing with logistic differential equations. You guys mentioned the other day that in biology, you guys talk about carrying capacity and things like that. Well, so the first thing I want to talk about is just the scenario. I want to talk about a real quick scenario about what happens when we're dealing with a logistic differential equation. But essentially, the common examples that get used with these are like a rumor spreading at school, or like a bunny rabbit population growing on an island with limited space and limited resources. Those are kind of the two scenarios that come up when logistic differential equations first get introduced. Like, you're always going to have an initial amount of, let's say, bunnies, or initial amount of people that start the rumor, or whatever the case may be. But there's always going to be some sort of limit to how many bunnies can spread on the island, or how many people can even hear the rumor, and that's called the carrying capacity. Like, you're capped, if you will. And so what happens is, the way the graph always works is it's always going to start growing exponentially, like really quickly. Then it's going to start leveling off. And this is what the graph of a logistic differential equation is always going to look like right here, where it's always increasing, but the first part is going to be concave up, the second part is going to be concave down. And you're capped by that limit. Like, there's only so many students in school that can hear the rumor. As the bunny rabbit population starts to grow, maybe now there's limited resources where the population's still growing, but now it's not growing as quickly. Or there's only so much space that can contain the bunnies. Those are the kind of scenarios that get brought up. So there are two different formulas that you guys might come across. All of the problems that I've seen, the problems have already been set up in one of these two forms. I did watch a video where a guy said he has seen questions where students had to manipulate to get into this form, but I don't know if that was from quite a while ago, because I've been told to only look over the more recent materials. And so these are the two forms you're going to have to be able to recognize. They mean the same exact thing, okay? And I want to explain how they mean the same exact thing. But first, in these two forms, L, this value L, there's really two key things to know. L is the carrying capacity. L is the carrying capacity. That's the maximum amount of people that could hear the rumor, or the maximum amount of bunnies on the island, if you will. And so notice that L can be in one or two places depending upon how the formula looks. I'm going to explain why we can manipulate to get these two equations to be the same. The second big thing, is the rate at which the population is growing, so dy dt, is always the largest at half of the carrying capacity. It's always the largest at half of L. So it's biggest at 1/2 of L, always. So these are the two really important things that we need to understand. We need to know what the graph looks like, and we need to know these two things here. The reason these two equations basically mean the same thing is, okay, so K stands for some arbitrary constant. K stands for some value. We don't know what it is when the problem starts, okay? Well, to manipulate, what we can do inside of the parentheses here to make it look like the one on the right, we can multiply inside the parentheses by L. Like, we can multiply the parentheses by L. But to combat that, we would then divide this component out here by L. And so all I've done is multiply one part by L and divided the other part by L. Well, if you look in the parentheses, the L's would cancel, and that's where that Y comes from. And then L times 1 is just L. And then K is a value that we don't know. It's an arbitrary constant. And when you divide it by a number, then it just becomes a different arbitrary constant. So this K value would just be different than that initial K value there. And we talked about that with moving that C from the exponent out in front when we did exponentials. So I kind of scoured and looked through a bunch of resources and materials and found 4 problems, 4 multiple choice questions. And these are going to be non-calculator. And I tried to find 4 different types of questions. And I tried to find 2 that use the first formula and 2 that use the second formula, just to get a pretty good range of the types of questions you might come across with these, okay? So the first one, and you could pause and try these 4 questions and see how you do and then listen. I mean, that's up to you. But I'm just going to read the question and kind of explain the problem. So the number of antibodies, Y, in a patient's bloodstream at time t is increasing according to a logistic differential equation. Which of the following could be the differential equation? So this question is just them seeing, can you recognize the form? Do you know the form that it would have to be? And so we're really just trying to match up one of these 2 equations. Well, I notice I don't see a fraction, so I'm really trying to get it into this second form here. So some K value, which that's what the 0.025 is, times Y, and then times some number minus Y. And so you can match that up with E right here. This is just them seeing, do you know what the logistic differential equation form is to begin with? Pretty straightforward. 27. The number of students in a cafeteria is modeled by the function P that satisfies the logistic differential equation, and then they give it to you right here. So 1 over 2,000 would be our K value, where T is time in seconds and P of 0 is 25. So that means the initial amount of students is 25. What's the greatest rate of change in students per second of the number of students in the cafeteria? So understand the question here. It's saying, what is the greatest rate of change? They're basically saying, what's the biggest value of dp dt that we would get? Well, this is us using the second key idea here. The rate of change is always the biggest at half of L. Well, L is this 200 value right here. The trick answer on this problem is 100. That's the trick answer. The greatest rate of change will happen when at half of 200. So when there's 100 students in the cafeteria, but it's not asking at how many students will the rate of change be the greatest. It's saying, what is the greatest rate of change? So we know this number will be the biggest when P is 100. So we need to plug 100 in for the P values. So we're looking for dp dt when P is 100. So we're just plugging 100 in for those P's. So 1 over 2,000 times 100, and then times 200 minus 100. So another 100. And we just got to do some mental math. So this would be 10,000 over 2,000. So 5. 5 students per second. So just make sure you understand the question, because C I could see being picked quite a bit. 28. N satisfies the logistic differential equation as followed right here, where n of 0 is 105. Which of the following statements is false? So 3 of these things are true. Now, it's important to look. Notice they're talking about limits and the first derivative and the second derivative. Let's get an idea of what this graph looks like to begin with. So initially, we have 105, and our carrying capacity is 850. That's going to be our horizontal asymptote. So the graph's going to start at 105. It's going to go exponentially till it gets to 425. Then it's going to level out. Notice I said 425 because that's half of L, half of the carrying capacity. So I know that where that point of concavity changes, where the concavity changes is at 425. because that's going to be the biggest slope there. I didn't do a very good job of, or maybe I did. Yeah, that makes sense, because we're starting at 105. Okay, so now I can look at the questions. It says as t goes to infinity, so as x or t gets really big, then the limit is approaching 850. And yeah, this graph is approaching 850. Cierto. dn dt has a maximum value when n is 105. Well, that's not going to be true because it's going to have a maximum value when n is 425. So I already know the answer, but I want to talk about the other two things. It says the second derivative is 0 when n is 425. Well, notice I said it changes concavity right here at 425. At inflection points, our second derivative is 0. And so that one's true. When n is above 425, so everything up here, let's see, dn dt is greater than 0, so that means this function's increasing. That's true. And then the second derivative is less than 0, so concave down, which is also true. So true. So we know B. And the last one, similar type of question. Wolves modeled by P grows according to the logistic differential equation as given, where T is in years and P of 0 is 1,000. Which of the following statements are true? Which of the following statements are true? Well, so kind of like the last one, the limit of P as T goes to infinity equals 5,000. That's what our carrying capacity is. We could see that right here. So we know that's going to be true. And you can sketch a graph on this one too, if it would help. We're starting at 1,000. The maximum is 5,000. And our graph goes like that. dp dt is positive for t greater than 0. Basically, this is saying P is always increasing. That's true. Always increasing. And then the second derivative is positive for t greater than 0. Well, that's not true. It's positive till you get to 2,500, and then it's negative. So that's false. So 1 and 2 only. See. So they're not very difficult questions if you know basically 3 things. What the graph looks like, L is the carrying capacity, and the rate of change of your function is biggest at half of L. Let me know if you have any questions. Peace out.